So we'll finish this section off with one last example. So let's read it carefully. We've got, looks like we've got some cars involved, car A and car B. So that's just, there's two cars and we're labeling them A and B. So one of them is traveling west and we're given the speed, 50 miles per hour, and the other one is traveling north and we're also given the speed at 60 miles per hour. Now, with just that first sentence, it's a bit premature to now try to draw a picture because it's not going to be clear what you actually want to draw, where these cars are relative to one another. But when you read the next sentence, that gets clarified. So both are headed towards the same intersection of two roads. So that actually clarifies it. If they're both headed towards an intersection and one of the cars is heading west and the other one's heading north, that gives you enough to get a picture of what's happening. So I'm going to sketch one of the roads here and sketch the other road here. So you've got something like that, right? Let's say car A is over here. Not the best drawing in the world, but again, it doesn't need to be, right? That's my car. And then car B is heading north towards that intersection. That could be car B there. And we got the wheels. And, well, they're headed towards the intersection, right? So this car A is traveling west at 50 miles per hour. So jot that down. And then car B is traveling north at 60 miles per hour. So just so we can get that information processed. And, well, what else does it say? Well, the next sentence is basically the question. At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? So at a certain point in time, car A is going to be 0.3 of a mile away from this intersection. So, the distance between car A and the intersection will be 0.3 miles, and the distance between car B and the intersection along this north-south running road is going to be 0.4 miles. And we want to know at that exact point in time, how fast are the cars approaching each other? And one thing that's worth thinking about for the moment is, why is this not just as straightforward as just adding their speeds together? Because why wouldn't you just say, okay, well, car A is driving at 60 miles per hour, car A is driving at 50 miles per hour, and car B is driving at 60 miles per hour. Why can't we just add the speeds and get 110 miles per hour and say that the cars are going to be simply approaching each other at 110 miles per hour? That would fail to take into account which direction the vehicles are driving in. If you were going to add the speeds, that would be under the assumption that the cars are driving straight towards each other, in which case they would be approaching each other much faster than they are in this case. So really what you're asked for here, when they say what rate are the cars approaching each other, that means there's a distance between the cars, right? If you were to say that's that point right at the front of the car, let's say that's the location of the car, car B, and then this point right here, right at the front of car A, that can be the location of car B. What we really want to know is how fast are they approaching each other in the sense of the distance between them being measured diagonally. So how fast is this distance changing? That's really the question over time, right? And we're given information about the rates of change of two other distances in this picture, right? If car A is traveling west at 50 miles per hour, that tells you how fast this horizontal distance is changing. So that argues in favor of giving that distance a variable. So how would we call that x? Or call it whatever you like, but I'm going to write the letter x. And then we can measure this distance here between car B and the intersection as y. And then we should also measure the distance between the two cars, since that's the quantity whose rate of change we're interested in. So let's give that a name. Call it Z, just to stick with the theme of what I've been doing. And that's going to be a good start. Those are probably going to be the variables that we want to use. And since it's an intersection, it doesn't strictly say it in the question, but I think it's fairly reasonable to assume that the intersection of the two roads intersect at a 90-degree angle, unless stated otherwise. If you're given a problem with an intersection involved with two roads, because this is a popular template for related rates problems. So if you're dealing with an intersection, assume that the roads intersect at a right angle. That's usually going to be important. Okay, so let's officially state what these variables are. So we can say x is, well, it's the distance between car A and the intersection. So we can fill that in. And let's specify the units, right? Since the distance is measured in miles here and measured in miles here as well, we should probably stick with miles for our units of measurement for distance. So let's go with that. And then y, as we just said, y is going to be the distance between car B and the intersection. And again, we'll stay in the unit of miles. That makes the most sense here. And then lastly, z is the distance between the cars. And that's also going to be in miles. Okay, so notice that did take me a minute or so to write those out, and the reason I'm doing this so consistently in the problems is I'm really trying to set a good example for you guys. I want you guys to get in the habit of writing out exactly what your variables mean whenever you do a related rates problem. I promise you it'll make this learning experience go much better. It'll improve your success rate with these problems, and it'll just make everything go much more smoothly if you take the time to be clear about what you mean early on in the problem. Okay, so now that we've got those variables laid out, that's probably going to be enough, but we can find out for sure by translating the problem. And if we're able to do it, then we probably have all the variables we need. So what does the problem give us, and what does the problem ask for? So, well, we're told that car A is traveling west at 50 miles per hour. So how can you express this as a rate of change? Well, what's happening to the variable x as this car A heads west? Well, x is going to be a quantity that's shrinking. So that's why this is wrong. If I were to write dx dt is equal to 50, that's not correct. Because if I write this down, what I'm really saying is that x is growing. Right? If it has a positive derivative, that means the slopes of the tangent lines to the graph are going to be positive, which means the function's increasing. So for that reason, this is not going to work. But that's okay, because all we need to do is change it with a negative sign. Really? Because if x is going to be shrinking as car A drives west towards the intersection, and if the rate at which car A is moving is 50 miles per hour, then that means that the rate at which x is shrinking is 50 miles per hour. So if we agree that time is measured in hours, and we already have that x is measured in miles, then this is the correct choice. That's the correct way to express this 50 miles per hour as a rate of change. And then for this 60 miles per hour for car B, just interpret that as y is shrinking at a rate of 60 miles per hour. So we can say, and dy dt is equal to negative 60. So that's how we'll interpret those rates of change. Now what are we asked for? We're asked for what is the rate at which z is changing with respect to time, right? We want dz dt. And we want it at the particular moment in time. Well, when car A is 0.3 miles from the intersection, that means x would be 0.3, and car B is 0.4 miles from the intersection. That would mean y is equal to 0.4. So we can say when x is 0.3 and y is 0.4. Oops, I guess a little off the screen, so I meant to have that up a bit higher. So this is what we want, right? dz dt. We want it at the particular moment in time when x is 0.3 and y is 0.4. So this is the translation of the problem, and now we're ready to solve it. But we need a relationship between our variables. Right? We need a relationship between z, x, and y. And the fact that the intersection's a right angle, that's what makes this doable. That's what gives us a pretty natural relationship between x, y, and z. We can use the Pythagorean theorem to say that x squared plus y squared is equal to z squared. So that's how we'll start this. By the Pythagorean theorem, we have that x squared plus y squared is equal to z squared. All right, so we're going to just jump in and take the derivative of both sides with respect to time. Right, so we'll have the derivative with respect to time of x squared plus y squared is equal to the derivative with respect to time of z squared. So how are we going to differentiate all of these terms? Just each one of them, use the power rule to differentiate the outside function, and then based on the chain rule, we need to multiply by the derivative of the inside function afterwards, with respect to time, of course. So let's start with the x squared term. Well, the x squared derivative with respect to t is going to be 2x. But then by the chain rule, we multiply by the derivative of the inside function, which is x. So we got 2x dx dt. Now for the y squared term, our derivative is going to be 2y. And then of course we multiply by the derivative with respect to time. On the right hand side, you can kind of see the pattern here, right? Derivative of z squared, derivative is going to be 2z, but then multiplied by the derivative of the inside function. So we're going to get 2z dz dt, right? And that's what we're going to get. And right away, you probably notice that each of these terms have a common factor of 2. So we could divide through the equation by 2, or divide everything by 2, or multiply by half, however you want to phrase it, and then we'll make this a bit simpler. Then we'll get x dx dt plus y dy dt is equal to z dz dt. So it gets a little bit simpler. Now, what's next? Well, we want to isolate for the quantity that we're looking for, which is dz dt in this case, right? That's the quantity that we're looking for. We want to know what is dz dt. So take this relationship that we now have between the rates of change and, well, solve for dz dt. What you're going to get is the following. Dz dt, well, I'm going to have to divide both sides by z, right? So multiply both sides of the equation by 1 over z, and I'm going to get 1 over z times x dx dt plus y dy dt. So that's what I get if I solve for dz dt, and now it's a matter of plugging everything in. So, well, let's just take inventory here. X, we have a value for 0.3. dx dt, we have a value for, it's negative 50. Y, we know is 0.4 at the point in time we care about. dy dt, that's going to be negative 60. What about z? We don't have a value for z. That's a bit of a fly in the ointment, so to speak. So how do we deal with that? Well, that's going to be one of those cases where we have to take a snapshot of our situation, right? Again, if you think of this as a video, a motion picture, and you take a snapshot right at the point in time when x is 0.3 and y is 0.4,